Hello everyone, thank you for giving me an opportunity to report our work. Our work focuses on learning the interpretation of the emotion speech signal. I'm Jianfeng and from Hangzhou Innovation Institute, Beihang University. This report mainly includes the following: 1. Introduction. 2. Related work. 3. The proposed approach. 4. Experiments and results. 5. Future work. 6. Conclusion. 1. Introduction. There emerged a trend towards deriving a deep representation of the input signal directly from the raw data. Deep representation learning has made a great improvement in several fields, especially in learning image representation. There are a lot of researchers have devoted to complete the recognition or prediction tasks using different deep networks. Inspired by the success of image restoration, a 1D deep encoder-decoder was designed. Our key contributions are as follows: 1. Complete the design of 1D deep encoder-decoder. 2. Adopt a different LBS in encoder-decoder. 3. Develop a dual training mechanism. The results show that the desired architecture can learn deep representation and reconstruct the speech signal successfully. Related work. Deep representation learning has made a great stride over the last several years, especially in image restoration. We only list several great works. Learning deep feature from raw speech waveform to implement speech-related tasks has also attracted increasing attention of many researchers. The following is great works have made by other researchers several years ago. 3. The proposed approach. The 1D convolution layer plays the role of a feature extractor and learn the local features. The convolution will produce a feature map by computing the dot product between the entry of the filter and the input. The 1D convolution can be expressed as the formula 1, and the deconvolution can be expressed as the formula 2. The 1D pooling layer performs the nonlinear downsampling function and reduces the resolution of the feature. Max pooling will partition the input into a set of non-overlapping regions and output the maximum value of each sub-region. The feature produced by max pooling layer can be expressed as the formula 3. Figure 1 illustrates the 1D max pooling and unpooling. Inspired by the idea of graphing, hard version pooling was used to output the maximal value of each pooling region in encoder, and upsampling to repeat the maximal value in each unpooling region in decoder. The location of the maximal value in each pooling region in encoder was handled to the corresponding unpooling region in decoder by mask. the value of a maximum value location of the pooling region is 1 in the mask, and the value of the other location is 0. Therefore, the reconstructed signal in an unpooling region can be represented as Formula 4 and 5. Deep radio learning can ease the training of a deep neural network. The skip connections in a LB are connections which skips one or several layers and connects to the next available layer. Different LBS were used in encoder and decoder to ease the training of the desired very deep encoder decoders. LB can be expressed in form. The figure 2 illustrates the radio learning blocks. Architecture. The DI architecture consists of 2 parts, the encoder and decoder. The encoder is formed by a stack of convolution and pooling layers. The decoder is built by the same number of deconvolution and unpooling layers. Figure 3 is the overall architecture of the desired 1D deep deconvolution encoder and decoder. The upper half of the architecture is an encoder. The bottom half of the architecture is a decoder. The exact location of the maximum value in the pooled receptive field is handled from a layer of encoder to the corresponding layer of decoder. Optimization algorithm. The aim of a hyperparameter optimization is choosing a set of hyperparameters from a deep architecture. An optimization algorithm will find the best fitting model by solving a convex minimization or concave maximization problem. Regularization methods. Overfitting always occurs when the deep architecture is very complex, especially when deep network has too many parameters related to the numbers of observations. Our work might use the weight decay and the earlier stopping to combat overfitting. Experiments and results. Database introduction. In our experiments, we only used 2 databases, the Boolean emulsion databases and the Sieve databases. Boolean emulsion databases. The Boolean emulsion database, which was recorded in 25, provides labeled audio clips and sim analysis results. These acted emotional utterances were spoken by 10 professional actors in an angry, boredom, disgust, fear, happy, natural, and sadness way. There are 535 sentences of the utterance, which come from everyday communication and can be interpretable in all appealed emotions. Sieve database. The Sieve database was released in April 2011 and provides audio, visual data, and other analysis data. It consists of 480 written English utterances, which is expressed by for native English male actors in 7 different emotions. The emotions have been described in discrete categories: angry, disgust, fear, happiness, sadness, surprise, and nature. In experiments, each database was split into 2 sets. One is training set, which takes 80% of the clips, and the other one is testing set, which takes the remaining 20% of the clips. Date pre-processing. The audio clips of each database vary in sample rate and length. The sample rate of audio clips used in the experiments in 16 kHz, so the audio clips of the saved database are all resampled to 16 kHz. All the raw audio clips are segmented to 4 echelons. At 16 kHz sampling rates, they can be represented as a 64,000 dimension vectors. The audio clips of the 2 selected databases are truncated and panned up to the length of 64,000. Then all audio data are pre-processed to have 0 means and unit variance. To use the hard softmax, all audio data are mapped to 0 and 1. The dared 1D deep convolution encoder-decoder was tried. Firstly, earlier stopping is adopted to combat the overfitting, while the monitored quality stops improving after the patience, the training will stop. The patience is the number of encores with no improvement of the monitored quantity. In the pre-training, the monitored quantity is validation accuracy. The patience is 7 to 8. After the pre-training, the decoder of the designed 1D deep convolution encoder-decoder was fine-tuned separately. The main steps of the fine-tuning are as follows. 1. Save weights of the 1D deep convolution encoder-decoder after the pre-training. 2. Transfer the learned feature of the desired 1D deep convolution encoder-decoder to the encoder. Save the prediction of the experiment date using the decoder. Transfer the learned feature to the decoder and fine-tune the decoder using the prediction at the experiment date. Early stopping is also used to combat the overfitting during fine-tune. In experiments, the fine-tune lasted much longer than training. Figure 4 illustrates the pre-training and the fine-tuning. Experiments results on Boolean emotion database. The experiments results on Boolean emotion database are shown in Table 1. From the table, we can see that the training loss and the testing loss in fine-tuning are much smaller than that in pre-training. The training and validation losses in pre-training and fine-tuning over encores on Boolean emotion database are illustrated in Figure 5. From the figures, we can see that the training and validation losses in fine-tuning are significantly smaller than that in pre-training. The waveform of the original signal and the reconstruction produced by pre-trained model and the fine-tuned model are illustrated in Figure 6. We can see that the waveforms of the reconstruction produced by the fine-tuned model have much higher fidelity when compared to length of the signal returned by the pre-trained model. Experimental results on saved database. The experimental results on saved database are shown in Table 2. We can see that the training loss and testing loss of fine-tuning are much smaller than that of the pre-training. The training and validation losses in pre-training and fine-tuning over encode on saved database are shown in Figure 7. These figures are show that the training and validation loss in fine-tuning are also smaller than that in pre-training. The waveform of the original signal and the reconstruction returned by the pre-trained model and the fine-tuned model are illustrated in Figure 8. We can see that the waveform of the signal produced by fine-tuned model have much higher fidelity than that of the reconstruction produced by the pre-trained model. Results analysis. The loss of the desired 1D deep convolution encoder-decoder as a whole contains 3 parts. In pre-training, the 1D deconvolution encoder-decoder will be trained as a whole. So, the loss is composed 3 parts, but in fine-tuning, the decoder is trained separately, so the loss only consists of 1 part. The location information related to the maximum value will be handled to the decoder by transfer filter. Therefore, the training and validation losses in fine-tuning are significantly smaller than that in pre-training in our experiments. Future work. The DI 1D deep convolutional encoder-decoder has obtained better results in our experiments, and the waveform of the speech restoration has high fidelity. But there are many aspects worthy of further discussion and study. 1. In our experiments, only the maximal value of a pooling region was restored correctly by unpooling. So how to restore all the value of a pooling region by unpooling deserves deeply study. 2. To restore a speech signal from convoluted filter accurately, the same filter adopted in convolution should be applied in deconvolution. So how to handle information of the convolutional kernel to the deconvolution layer also need for further research. 3. Comparing to the distortion of a restored emote, the outer of the reconstruction speech signal is more likely to be perceived. So how to detect the distortion of the restored speech signal is worth delving into. 4. As we know, the tolerance level of a person to animate is higher than that to speech. So how to measure the distortion level also need for further research. 6. Conclusion. In our work, we designed 1D deep convolutional encoder-decoder to learn high-level representation from raw audio clips. Further, we adopt a dual training mechanism to train the desired architecture, which can leverage the training in a more effective way. By using our proposed mechanism, the loss dropped dramatically and the reconstruction has much higher fidelity. Results show that the desired architecture can learn deep representation from wrong speech signal and model high-level abstraction of the speech signal from the wrong audio clips. Acknowledgement. Thank you.